We've already learned everything we need to know in section 1, but we can do these slope field problems on our calculators, which is kind of nice. But you will be asked, it's not likely, you most definitely will be asked to sketch a slope field by hand on the test. So you do need to know how to do that. But if it is the calculator portion, they might be talking about a slope field and expect you to be able to do it on a calculator so that you can kind of analyze very quickly what's going on. So you do also need to know how to make a slope field on your graphing calculator. So that's what we're going to do for now. So practice both, and all of these equations that you see, or differential equations that you see, are what we have done so far in this section, all of those, believe it or not. So we're just going to go back and redo all of those on the calculator to take a look at the slope field for them. So grab your calculator and bring up the graph. And we need to do some different things than we normally do when we're graphing. So on the graph screen, press menu. And then you will go to, let's see, it's graph type or something like that. What does it say? There you go. The bottom one says diff-EQ, and that's differential equations. So that's the one we want to pick. So mine says graph entry and edit, but you're going to do graph type. So notice that the notation there says, first of all, you got a little checkbox here. You can turn this this graph on and off as needed. So you can enter in a bunch of these and just uncheck them if you don't want to see them anymore. This is y1 prime right there. So I'll explain this y1 thing here in a minute. For that first one, we're just typing in y prime equals x. So in this box, we can type in x, and then go ahead and graph it, and it gives us that slope field automatically. Now, you can also change the settings. You can change the density of the tick marks. You can also change, I think, the length of the tick marks and how many they will show. The default on these calculators is usually pretty good, so we're just going to let that be. Now, if you want to put a particular solution on here, then press the tab button. That will bring your window back up, and you're going to want to press up to get back to y1. Then, if you want to put a particular solution on there, you have an ordered pair that you can enter in. If you want to enter in more than one ordered pair, then you're going to click on this little guy over here, and it'll bring up a window of several ordered pairs that you can type in. So let's just try one of them. Let's try like 3, 3. And then hit OK, and I'll get out of that window, and there we go. It gives you the dot for 3, 3, and then it gives you almost like a scatter plot looking thing. It just sort of generates not an actual function, but its best approximation of what would be a function for this graph. And you can see as this graph kind of takes off, the dots get farther and farther apart. So there's one particular solution. We can do another one if you want to. We might as well because the practice is good. So we're going to press tab and then up to get back to our y1. And then in the second window, I'll do like -4, 0 just to see what happens. And then hit OK and get out of there. And there you go. So with the differential equation y prime equals x, we talked about this. When we integrate this thing, it would wind up being a quadratic equation, which always graphs a parabola, and that's exactly what we're seeing here. So hopefully on the calculator, maybe more so than the graphs that you were making, you can kind of see what this slope field is actually doing and how these functions will look. So let's go on to the second one. We have y prime equals y. Now to do that, what I want to do is I'm going to press tab and then go back up and uncheck that first one, because maybe I'm doing a bunch of these and I don't want to have to redo them every single time I go on to the next problem. So I just uncheck that one and it stays there, but it goes away. So then I press down a couple times and it goes to y2. Now y2 is checked, so when I type in that, it will give me this graph. But I have to type in y on this one. It says y prime equals y. But here's the thing. If you don't type in the actual y that you're on, it's not going to give you anything. So like if you were to type in y and press enter, nothing would happen. what you need to do is type in y2 because we're on function, or we're on the second one of our thing. You have to include the number along with the y. Then when you press enter, wrong number of initial conditions. All right, so what that means is I need to go up here, and I got this problem because I got this grayed out 3. So I'm not going to be able to do what I want to do here. So I'm going to close that. No, I don't want to save it. I'll bring up another graph and menu. There we go, differential equation. All right, so I'm on y1 because I just restarted it with the initial conditions that I had that were grayed out. I couldn't change them, so I had to start over. So I'm typing in y and 1. Now I press enter, and now it does give me that slope field. And with this one, you can kind of tell that as we move from left to right, we're going to probably be kind of close to the x-axis, and then it will sort of diverge away from the x-axis, no matter where we are, okay? We could put an initial condition on here, like maybe here, and you could kind of see how this thing will follow along that curve. It'll sort of have a path like that. Or I could put an initial, or a condition right here, and then I would have a graph that looks like this. Or if I put a dot here, then my graph would kind of follow along that line. All right? Try to visualize what these things look like once you see the graph. So let's go on to the next one, y prime equals x plus y. And I want to try this again. I'm going to go to y1 and uncheck it. And then go to y2 and just type in x plus, this time it's y2. And it didn't do anything for me. All right, that figures. So let me get out of there. Escape, escape. There we go. No, sorry. So it's x plus y, 1. There you go. So on this one, this is one of the first ones that we did completely on that entire window. If you go back in your notes, you'll see that we did that full thing. And we had the situation where we had like a line that sort of went all the way through this, and then we had that zero slope all the way kind of through there. That line is going to prevent me from crossing over from here to here. If I'm over here, my graph is going to kind of do this. It will never make it over here because of the little line that we had going all the way down. I think it was like through -1 or something. I don't remember exactly. If we're on this side, we're going to kind of come down and curve around. We'll curl around like this, and we'll never wind up over here because of that boundary line that was sort of created. So I want to put a couple of conditions on there to show you exactly what I'm talking about. So I'll pick a spot over here, like maybe 5, 3 or something. So tab, and okay, you are really making me happy. Let me restart this, and we'll redo what I've been doing. Okay, so like 5, 3, and then I'll pick another one that's over in this region down here in the negatives, so like -2 and maybe -6. So if you notice on this one, we did have that kind of boundary line that we said kind of acted like an asymptote, even though it's really not in this case. If we're slightly on this side of that boundary line, like this dot right here puts me on like the north side of that boundary line, it still approaches that horizontal asymptote, but over here it follows this part of the slope field. If I'm on this side of the boundary line, it follows this part of the slope field, and it completely goes away from the other graph. So you can wind up with two very different situations just depending on whatever condition you're given based on the slope field that we have. So watch for little boundaries like that one that we had on that one problem. When you graph it, when you graph the particular solution, the graph would be an asymptote. Yes, what you're seeing is kind of an asymptote, like a slant asymptote. Okay? But only on this side. On this side, that's not the case. This thing diverges from that asymptote on both sides because of the slope field. So I can put a bunch of other conditions on here and see that this side always diverges downward from that asymptote. This side always quickly curves upward from that asymptote. These are two completely different graphs here for the same exact original differential equation, just based on the particular solution that they're giving me. Okay? So take a look at what we had compared to what the calculator came up with. This took us a while to come up with. This was instantaneous. Obviously, it's way better to be able to do this in the calculator quickly to come up with what the graph's going to look like. But you can kind of see that asymptote sitting right here. So if I'm just to this side, eventually it will curl off and go up. If I'm just below that asymptote, I'm going to curl off and go down for forever. So if my initial value is here, then I'll have a slope that kind of matches that there, and then I'll be about horizontal through here, because those are all horizontal, and then I kind of go up and follow that asymptote. So there's my graph. But if I'm on the other side, like maybe I'm here, then I have a slope that's kind of doing this, and it curls downward, and it just follows that asymptote on that side. That's exactly what is being graphed here, it's just with a bigger window. So just make sure that you're aware of asymptotes when they appear. Make sure you're aware of horizontal situations when they appear, so that when you graph in those solutions, you match up appropriately. Okay, this time we'll do x minus y. I'm just going to keep exactly what I had, change the slope field, and now I have two different, those same two initial conditions are on this particular graph for these particular solutions. All I've done is change from y prime equals x plus y to y prime equals x minus y. Notice that I have an asymptote looking situation here. Both of my initial conditions to give me my particular solutions fell on the bottom side of that asymptote, which is why both of them kind of follow along here. If I pick an ordered pair in this region, you can kind of see how this will curl down and then curl around and then go off along that asymptote. So let me pick another one. What do you think? Give me an ordered pair that would make me have that top part. Negative 5, 1? Okay. And there you go. So all of them eventually converge onto that asymptote. But if I'm going the other way, all of them diverge away from the asymptote. It just depends on which side of the asymptote they're on that they curl one way or the other. So I want to also do this one, x y prime minus 3y equals 0. What should we do on that one first? Yeah, we got to solve for y prime there. So on this one, I'm going to add 3y to both sides. X y prime equals 3y, and then divide both sides by x. So now I can enter that one in, and I'm just going to reuse the same graph like I did before. So I'll delete all those, and I'll just type in 3, and it has to be y1, remember, divided by x. Hit enter, and it gives me that graph. Now, something interesting is happening here. Obviously, it looks like everything is kind of originating from the origin, if you really look at that, and that's exactly what's happening, actually. Notice that the blue one comes in and stops. The green one comes in and stops. The red one goes out and diverges away from the x-axis. But none of them proceed beyond here. Why is that? What kind of asymptote? How do you know it's a vertical asymptote? Yeah, you're dividing by x here. So when x is 0, you have a vertical asymptote. When y is 0, you have a horizontal asymptote. So in this case, yeah, that's what you have. So as we approach that vertical asymptote, the slopes are getting lower and lower, actually. They're getting less and less severe, which is kind of an interesting thing. Usually you take off right? Like the slopes become greater and greater, steeper and steeper until you hit that vertical asymptote. That's not what's happening here. The slopes are actually getting smaller and smaller until eventually you hit that vertical asymptote. Now once you hit a vertical asymptote, you can't cross it, which is why this blue one comes to a dead halt right there. And the green one comes to a halt right there. And the red one, if I'm going the other way, also comes to a halt right there. So if I don't have those other two initial conditions on there, all you would see would be this portion of the red graph, and that's it. It can't cross. Because of the fact that I have an initial value on this side of that vertical asymptote, all I get is this side of the graph, and that's it. But if I put an initial value on this side of the vertical asymptote, I get this side of the graph, and that's it. Okay? So don't let this one deceive you. There's actually 3 separate graphs here. All of them stop at the y-axis because of a vertical asymptote. All right, I do want to show you this last one because it's also interesting, and I'll leave these 3 on here like before. So let's change that. I just delete all these to 2x plus, and then remember, again, it has to be y1. Okay, so on this one more time, you probably have some sort of asymptote situation happening in here. You can see how these are all getting pulled together up here off of the screen. On one side of the asymptote, it sort of diverges down. On the other side of the asymptote, we diverge up. So on the slope fields, there's definitely a lot to look at, and it really helps to picture what's going on if you enter it into a calculator so that you can quickly see what's happening on either side. But without those particular solutions on there, hopefully you can kind of read the slope field just as is so that you can put a particular solution on there if you're asked to do so by hand. Time.